Welcome back to Hexabot. In today's episode, we'll explore one of the most important devices in mechatronics engineering, the transformer. It's the reason we can efficiently transmit electricity over long distances and safely deliver it to homes, factories, and electronic devices. Understanding how a transformer works will help you master many fundamental concepts like electromagnetic induction, alternating current, voltage stepping, and more. This is part of our Mechatronics Engineering series, so if you haven't seen our previous episodes, we recommend checking those out first for better context. What is a transformer? A transformer is an electrical device used to change the voltage of an alternating current, AC, either stepping it up or down without changing its frequency. It works based on the principle of electromagnetic induction, first discovered by Michael Faraday in the 19th century. There are two major parts in a transformer: primary coil, connected to the input voltage; secondary coil, connected to the output voltage. Both coils are wound around a common ferromagnetic core. Why only AC works in a transformer? Let's first understand why alternating current, AC, is essential for a transformer to work. When AC flows through the primary coil, the current constantly changes direction, which causes the magnetic field to also change in both strength and direction. This changing magnetic field is what induces a voltage in the secondary coil. This is known as mutual induction. In contrast, direct current, DC, flows in only one direction. That means the magnetic field it creates is static and unchanging. No changing field means no induction in the secondary coil, so the transformer won't work. Basic working principle. Now let's take a closer look at how a transformer works, based on the principle of electromagnetic induction. When we send alternating current, AC, through a coil of wire called the primary winding, it doesn't just generate current, it creates a changing magnetic field around the coil. This is because the AC current is continuously changing direction and amplitude, and according to Ampere's law, a changing current creates a changing magnetic field. Now imagine placing a second coil of wire, called the secondary winding, near the primary coil. If the magnetic field from the primary coil can reach the secondary coil, something interesting happens. That changing magnetic field cuts through the turns of the secondary coil, and by Faraday's law of electromagnetic induction, it induces a voltage in the secondary coil. This is the core principle of how a transformer transfers energy without any direct electrical connection between the two coils. No electrons physically jump from one coil to the other, only the magnetic field does the job. There are three key factors that determine how effectively this energy transfer occurs: the number of turns in each coil. More turns in the secondary coil equals higher output voltage step up. Fewer turns in the secondary coil equals lower output voltage step down. The rate of change of the magnetic field. The faster the AC changes, the stronger the induced voltage. That's why transformers only work with AC, not DC. The coupling efficiency between the coils. If the coils are too far apart, or if the magnetic field is weak, much of the energy is lost. To increase efficiency, engineers insert a core made of laminated silicon steel between the two coils. This magnetic core serves two major purposes. It acts as a low-reluctance path, guiding the magnetic field from the primary coil directly into the secondary. It concentrates and amplifies the magnetic flux so that minimal energy is wasted. This design allows for compact, efficient voltage transformation with minimal heat loss. One of the reasons transformers are so reliable and long-lasting. Core design and energy losses. So far, we've seen that the magnetic core in a transformer plays a crucial role in guiding the magnetic field efficiently between the primary and secondary windings. But using a solid iron core isn't a perfect solution. Here's why. When the alternating magnetic field from the AC current flows through the core, it doesn't just passively move through it, induces eddy currents inside the metallic material. These are circular electric currents that swirl within the bulk of the iron core, perpendicular to the direction of the magnetic field. These eddy currents have two main downsides. They generate heat inside the core, wasting electrical energy in the form of thermal energy. They reduce the transformer's efficiency, especially in high-frequency applications. To overcome this issue, engineers use a laminated core design instead of a solid block. A laminated core is built from many thin sheets of silicon steel, each coated with a thin insulating layer, and stacked together to form the core. These layers are aligned so that the magnetic field can still pass through efficiently, but the flow of eddy currents across layers is disrupted. Why is this important? Because each steel layer is electrically insulated, the eddy currents are confined to very small loops within each sheet, greatly reducing their strength. This minimizes energy losses, known as core losses, making the transformer much more efficient. Additionally, laminated cores help reduce hysteresis losses, another type of energy loss that occurs as the magnetic domains in the core material realign back and forth with every AC cycle. So, in summary, although the core looks like a solid structure from the outside, it's actually made of carefully engineered layers to maximize magnetic performance while minimizing heat and energy loss. Voltage step up, step down. A transformer changes voltage based on the turns ratio between its primary and secondary coils. If the secondary coil has more turns than the primary, the transformer steps up the voltage. If the secondary has fewer turns, it steps down the voltage. The formula is V's over VP equals N's over NP. V's equals voltage on the secondary side, VP equals voltage on the primary side. N's equals number of turns in the secondary coil. NP equals number of turns in the primary coil. Step-up transformers increase voltage for long-distance power transmission to reduce energy loss, while step-down transformers lower voltage for safe use in homes and devices. Transformers are very efficient, usually above 95% with minimal energy loss. Transformers play a critical role in electrical power transmission. Electricity from power plants is generated at low voltage, but to transmit it over long distances, we must increase the voltage using a step-up transformer. Why? Because power loss P equals I squared R increases with current. By stepping up the voltage, we can reduce current, thus minimizing resistive losses in transmission lines. Once the electricity reaches cities, step-down transformers reduce the voltage again to a safe level for homes and industries. Types of transformers. There are many types of transformers depending on their use. Power transformers for grid transmission. Distribution transformers used on streets and neighborhoods. Isolation transformers for safety. Three-phase transformers used in industrial systems. Some are made from three separate single-phase units, while others are integrated into a single three-phase core. To sum up, a transformer transfers energy using electromagnetic induction, only works with AC due to changing magnetic fields, changes voltage level using the turns ratio, reduces power losses in long-distance transmission, plays a key role in safe and efficient power distribution. If you found this video helpful, don't forget to like, share, and subscribe to Hexabot for more deep dive mechatronics engineering content.